Good morning, everybody, and welcome back. For those that have managed to take some leave over the last 2 weeks during the school holidays, I hope you've come back refreshed and recharged and ready for the second half of the year. I acknowledge the traditional owners and their custodianship of the land on which we meet today. On behalf of the Sustainable Minerals Institute, I pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognise their valuable contributions to Australia and the global society. Today's presentation, Two Angles, Investigating Accidents for Lessons Learned, is delivered by Ben Seligmann, a research fellow in our mining industry safety health centre. Ben is a risk specialist, systems thinker and teacher. Over the last 10 years, he has worked in academia, engineering, consulting, HSE, risk and compliance across mining, infrastructure, healthcare, risk assessments in practice. His particular research interests are new frontiers of risk management, risk assessments in practice, modelling of accident scenarios, and trying to engage with the complexity of socio-technical industrial systems. His webinar today focuses on how we can generate more useful lessons from accident investigations. As usual, we will have the Q&A at the bottom of the screen. If you just click on that, and if you could pop in your questions as we go, feel free to do that as Ben is presenting. And then at the end of the presentation, I will open it up and I will then pass on and read your questions through to Ben, who can then answer them. So Ben, over to you.
Thanks, Neville, and welcome everyone. Thank you for coming. So originally this webinar was delivered for the Joint Chemical Engineering Committee, the Queensland chapter of IChemE, the Institute of Chemical Engineers, and also Engineers Australia. And I co-presented it with a man called Derek Herity, there he is up there, who's a Senior Health and Safety Manager at Laing O'Rourke. The first half of the presentation is some research outputs that he generated with some co-authors. And that was published in 2018. The second half of the presentation is some unpublished work from myself, which builds off his work. So we thought it would be interesting to present the two angles together. So the big idea, have you ever wondered how to get the best use out of your accident investigations? How to get the most useful set of lessons learned? Today, I'll present the outcomes of some research that explores this topic from two angles. Firstly, is there a link between the style and language of investigation method used and what you learn from it? If so, we should think carefully about which method to use. But how can we choose an investigation method to increase our chances of getting the most useful set of lessons learned? Using a method that gives richer accident descriptions is a step towards doing this. The second part of the presentation explores why certain investigation methods generate richer accident descriptions than others. So part one of the presentation is looking at how the style and language of accident reports affects the interpretation of them and the type of lessons learned you can extract from them. And this is the work that was contributed towards a journal paper that Derek published with some co-authors in 2018. Part two explores why one accident investigation method can generate richer descriptions than another, and why combining the results of different investigation methods can give richer accident descriptions as well. Now, considering how we interpret accident reports really matters, because the type of language used to describe the information in the reports can influence how we view the world. If we were to describe mistakes, for example, which cause accidents in the same manner as crimes, this has the potential to lead reports to become human-focused or human error-focused. Even though systems thinking approaches are reasonably widespread now across the industry, as opposed to merely human error focused methods, those who have moved to systems thinking approaches continue to use certain aspects of this type of old language. So the question that Derek asked himself was, can the style of the report used and the language employed influence the actions, the recommended actions that are suggested out of that report? So how did he investigate this? This research started with a real accident report that happened on a construction project of Derek's. What happened was, on Friday the 23rd of September in 2017, the door of a brine concentrator was being secured with nuts when an incident occurred. The tool being used, which was a torque multiplier, weighing almost 4 kilos, slipped from the nut it was being used to tighten and fell through a gap in the scaffold onto a level 16 meters below, where a team of insulators were carrying out particular work. I should say no one was hurt in this incident, but it was quite a near miss. Now, the goal was to study the effect of language and style of the accident reports on lessons learned. The original report from this accident, here it's called Report Variant 1, was identified as a linear and reductionistic style report. To this was added 2 additional and different report variants that Derek generated using the basic information associated with the incident. They were intentionally different in language and style than the original report. Report Variant 2 was the results of a SWOT analysis, that stands for Strengths, Weaknesses, Opportunities and Threats, performed on the work context around where the accident occurred. The SWOT focused on these 5 areas: the daily activity briefing, which is like a toolbox talk, personnel, tools and equipment, work environment, and task execution. Report Variant 3 was called the multiple stories approach. The content of the report was essentially the text of the interviews taken with key people involved in the incident. So after recruiting 93 participants for the study, each report variant was randomly assigned to a different participant. And the person or the participant was asked to suggest 3 actions that the company could take as a result of reading the report variant that they received. So out of that, there was almost 300 corrective actions proposed from the 93 participants. Now, these were coded or grouped into 2 main categories. The first was human or blame focused, and the second was systems focused, because this was the particular area of interest of concern in that work. To choose where to assign an action, the guidelines in the table on your screen now were used to apportion the actions. So for example, human or blame-focused actions included actions that were talking about punishing the people involved, or other non-punitive actions, but that were still focused on people, on the actions of individuals. Whereas systems-focused actions covered a range of things, including suggested changes to the physical workplace, changes to work practices, indirect changes to broader company practices, or alterations to documents. So here are some examples of the human-focused recommendations across the 3 report variants. You can see in the left-hand column the examples from each report variant. So actions focused on punishing the people involved included disciplinary action against the supervisors for the improper briefing that they conducted, or instant dismissal of the mechanical crew. Some other non-punitive actions included retraining the workers to comply with approved risk assessment statements, or better training on the appropriate use of tools. Now, some systems-focused recommendations across the 3 report variants. Actions that focused on changes to work practices included making it compulsory to fit all tools with lanyards, or introducing a weekly inspection of the scaffolding, because there was a particular problem with the scaffolding in this case. Actions that focused on indirect changes to company work practices included getting the management to reconsider commercial embargoes on issues related to safety, So in this case, there was a freeze on buying new tools. Hence, that's why they needed to use the torque multiplier in the first place. If they hadn't have, if there wasn't the freeze and they could get the tools they needed, they wouldn't have needed the torque multiplier. I think that was the implication. But the big question was, did the type of report actually have an effect on the actions suggested? Did the style and language of the report? And looking at the graph above, the short answer is yes, it did. This graph shows the percentage of human or blame-focused recommendations against the percent compared to the percentage of systems-focused recommendations provided for each report variant. The traditional approach, that was report variant 1, the linear reductionist style approach. The systems approach in the middle was the SWOT analysis, report variant 2, and the multiple stories approach was report variant 3. You can see that across these 3 report variants, the proportion of human or blame-focused actions was quite different. 27% of the actions of report 1 were of this type, but it was only 8% and 5% respectively for the SWOT and multiple stories. Conversely, the proportion of systems-focused actions therefore was much higher for the SWOT and for multiple stories than for the traditional approach. Therefore, Derek concluded that the language and style of the accident report did have an effect on the type of actions that were suggested out of it. So what can we conclude from this? What did he conclude from this? First of all, the language that we use has an influence on how we understand the world and what we suggest from it. Also, how you frame the investigation can box in the type of outcomes that you come up with. For example, human-focused language in the framing of the story can lead to an increase in human-focused actions. Moving away from linear stories allows for a much more comprehensive and richer narrative where all sides are listened to equally, such as in the multiple stories approach. And ultimately, the language used determines the level of engagement and the style of the response. In short, it seems worthwhile to carefully consider the language used in an accident report, since the actions extracted will be influenced by it. So now on to part 2. How does the type of investigation method affect how rich your accident description is? One of Derek's conclusions was that moving away from linear stories allows for a more comprehensive and richer narrative. And this raised some questions for me when I read it. First of all, are the SWOT and multiple stories reports actually richer than the traditional method? And what do I mean by richer? How would you measure that? And that led into the work I'm about to present to you. As I said, this work is unpublished and still undergoing analysis, but I wanted to share it with you now for 2 reasons. First of all, I thought you'd be interested. And second of all, to listen to your feedback and to hear what you think. And so in the Q&A later, please feel free to put in comments and suggestions as to what you think, how you think this work could be improved. Okay, it has been said that if you have rich accident descriptions, you're able to generate more useful lessons learned. But what generates rich accident descriptions? Generally speaking, accident investigation methods are used to generate accident descriptions. And today we're going to explore what is it about accident investigation methods that produce richer results compared to one another, and why combining the results of different methods produce richer results as well. But richness could mean many things to many people. So here we limit ourselves and we consider it to mean more information. Now, there are many ways to measure information, but here we will be using causal networks to represent accident descriptions. Now, we've converted the 3 accidents in Derek's paper, the ones that we talked about before, into causal networks to explore the differences between them, the richness of them, and what happens when you combine them. Based on this approach, we have defined richness to be the size of a causal network in terms of the number of nodes, the number of events, that represents an accident description. Now that sounds like gobbledygook to some, so let's see what that looks like. Here is accident report 1, which is, well, report variant 1. I'm going to call it accident report 1, AR1, from Derrick's 2018 paper as a causal network. Now, this is the network from the traditional method in that paper. Each node in the network, each little dot is an event, such as torque multiplier fell. The edges between the nodes and the direction of it, so the direction of the arrows, are the direction of what events cause other events. So node 12 here, this is the purple arrow, is the key event when the torque multiplier fell. This is what the SWOT analysis accident report looks like as a causal network. Node 28 here is the key event when the torque multiplier fell. You can see straight away that the SWOT analysis adds more detail, adds more nodes than the traditional method in AR1. AR1 had 15 nodes, whereas AR2 had 30 nodes. You can see n equals 30, number of nodes equals 30, down there. Therefore, according to our limited definition here, AR2 is richer than AR1. This network represents the multiple stories accident report. Here, node 44 is the key event when the torque multiplier fell. Now, AR3 had 45 nodes, which is 45 events. It is the richest accident description, except for the combined scenario, which I'll show next, followed by AR2 and then AR1. And this is what happens when you combine all three of them together and you remove duplicate events. So the combined scenario is the biggest and therefore the richest at 55 nodes or 55 events. Here, node 12, again, is the key event when the torque multiplier fell. So we've seen the different networks and what they look like when combined. And just to remind you, the number of nodes for each network to show the richness order is shown at the bottom of the next few slides. But what generates the richness between different methods and when you combine them? Here are some possible explanations. The scope. One method has a greater scope if it considers more classes of events or kinds of events than another. The density. For methods with identical scopes, one method can identify more events, meaning the density of the final description is higher. For example, one method might only capture 10 events to describe something, but another method with the same scope captures 20. The density of the second description is higher. Now, density has two sub-explanations. It can be influenced by the partitioning of a method, which is the number of categories for how events are classified, and also the granularity or the level of detail for how those events are described. I'll explain that a bit more later. And also whether the analyst is interpolating or not. The next explanation is what we're calling logical inclusions. One method logically allows for combinations of events that are excluded from other methods. For example, an accident report might have the event, Bob did a risk assessment, but another event in the report states that Jane noticed that Bob said he was going to do a risk assessment, but didn't actually do it. Now, these events are mutually exclusive. They can't both be true. A method that allows for events like this can produce richer descriptions than another that doesn't. And finally, extra or missed events. Regardless of the method, if everything else is the same, if one analyst just misses an event that another one gets, then the richness is higher in the second case. For today's talk, since we've only got 20 more minutes or so, we'll just talk about the scope and the density. So in order to actually measure the scope and the density between multiple descriptions of the same accident, there are three ways to interpret or define what we mean by them. We've measured each of these in turn to try and show you the biggest, richest picture we can. First of all, the method feature. The first is in terms of the scope. The first is what the scope says. First is what the scope according to what the method says about itself. If the method states what kinds of events it allows, then that is an indication of the range of events that are likely to be included in the results. Second of all, when you have the results, in terms of the event descriptions themselves, the kinds of events that do actually appear in the results are the real scope of the analysis. From studying the 3 accident descriptions in AR 1, 2, and 3, we have looked for themes and coded the kinds of events in an attempt to summarize what kinds of events were actually captured. If the results of a method has identified more kinds of events than another, you can say that the scope is bigger. We'll show this on a later slide. In terms of a network interpretation now, the average shortest path from all nodes with causes, which means at least one cause, back to nodes without any causes. That means the more events back up the causal chain you go from a key accident event, from where those purple arrows were pointing, the more chance the scope is bigger. This is because it's more likely that more kinds of events are included. Now, this measure is the weakest measure of scope. This is because it can only be meaningfully identified by comparing 2 networks describing the same accident, because the reason why the path is longer might be because of the density of the network, for example, which we'll cover next. Density is either due from the granularity of partitioning or from interpolation. Now, in terms of partitioning, from what the method says about itself, what categories does the method give for classifying events? I'll show an example below for the 3 methods. The more categories you have, the higher chance of a more dense description. And also, the granularity of the categories matter. That is, how much detail is allowed for describing each event. In terms of the event descriptions, when the events are coded, which means grouped into similar events, then the histogram of the codes for each network can be created. The number of events for each network applied to a certain code. And the shape of the distribution of that histogram, we believe, reflects the granularity of the method. The more uniform the distribution, the more granular the event descriptions. I'll show an example of this later. The Shannon entropy is a measure of how uniform a distribution is, and we have calculated it for all the networks we've analyzed here for comparison. In terms of interpretation, this can only be clearly identified if the method says anything about it, or if the analyst notes it was applied during the investigation process. It can't be identified just from the descriptions of the events or the network itself either. Now, in terms of the network interpretation of density, when 2 or more networks are compared, the density of one compared to another can be easily seen. You cannot tell if the density, as seen in the networks alone, can be explained by partitioning or by interpolation. And we'll see an example of this later. Now, I said we coded the events and we made a histogram. So here is the histogram for all the networks of the codes. And you can see the codes on the left there, the way we group the events together. Here we see a distribution of the codes applied to each network. From our analysis, we allocated 8 codes to the events across AR 1, 2, and 3. 1 code was allocated to each event. The x-axis shows the proportion of events in the relevant network for each code. For example, 20% of the events in AR1, this is the bottom row, related to the code communication, information, or knowledge. So that's how you read it. You can see that AR1 only covers 6 codes and doesn't touch organization or project management or people, relationships, and tasks. AR2, 3, and the combined network covers all of them. Another interesting feature of this figure is that the distribution of the codes across each network is different. AR1 is the least uniform, the most peaky. We think this means that it encourages the analyst to allocate events into fewer categories compared to the other methods. AR2 is more uniform than AR1, but less than AR3. Since SWOT specified event categories and multiple stories did not, SWOT is AR2 and multiple stories is AR3. This means it makes sense that the resulting distribution of event codes were less uniform for SWOT and more uniform for multiple stories. This was because there was simply not a filter for multiple stories. The events could belong anywhere, and they tended to. Now, to see the differences in scope between the different methods, let's go back to the combined network. Here is the combined network with nodes that AR1 contributed to it are highlighted. These are the green dots. So all the green dots, they come from AR1, from the traditional method. And the blue dots are those in the combined network that don't come from AR1. Now, this is what the red dots here are those from AR2, from the SWOT analysis. The causal pathways extend further back, further up the causal chain than AR1 do. This implies that the scope is likely bigger. And remember, all this is about trying to explore why there might be a difference in network size, different in richness between the networks. Here is the AR3 contribution to the combined network. It covers many of the same events as AR2, but has some branches that AR2 doesn't have. So for example, 38, 39, 41, 42, AR3 has. Conversely, AR2 has some branches that AR3 doesn't, such as nodes 23, 24, and 25 in the top right there. Now let's have a look at some differences in density to show you what I mean by that. Here is a snippet from the combined network, each showing the events contributed from AR1 in green, AR2 in red, and AR3 in yellow. Nodes 6 and 7 are there in AR1 and AR3, but not in AR2. AR3 also adds node 53. This is in the red circle. Similarly, node 48 is in AR3, but not in AR1 or AR2, and that's in the blue circle. Now, AR2 provides nodes in nodes 29, 30, and 34, but AR1 and AR3 do not. This is in the purple circle. These nodes, all of them in all these circles, are all in between other nodes that exist in other networks, and can therefore be seen as an increase in density. This increase is either due to higher granularity of partitioning or interpolation. You cannot tell just from the network representation which is the correct explanation. So now we're going to see all the results together. I'll go through this table carefully because there's a lot in it. And the purpose here is, again, to try and explain why we see an increase in richness from AR1 to AR2 to AR3 to the combined network. And that measure of richness is on the top row there in terms of the number of nodes. First of all, let's look at the scope. To explore what the methods say about what their scopes are, I've extracted some quotes from Derek's paper about each method. These are what they say about the kinds of events that were allowed in the door. The traditional method was human error focused. Events that are at the system level, such as resources constrained, are excluded in principle. The SWOT analysis has a wider stated scope than the traditional method. This is because the events from the SWOT analysis are generated through the lens of system level strengths, weaknesses, opportunities, and threats, not merely human error. The scope of the multiple stories approach was framed through aiming to capture each actor's account, which puts very few limits on what kinds of events are likely to appear in the final results. Thus, it looks like the scope of each method increases from the traditional method to SWOT to multiple stories. Now, the scope of the combined network cannot be determined from a method because there is not a method that directly generates the combined network. It is the product of combining the results, not the methods, of the traditional, the SWOT and the multiple stories approach. Now, go to the next line down, the number of codes. The coding based on the results supports this conclusion, except that the number of codes applicable to AR2 and AR3 is the same. Therefore, according to the codes used, the scope of AR2 and AR3 are greater than AR1, The combined network has the same amount of codes as AR2 and AR3, unsurprisingly, because it is built from them. Now, if we look at the network itself, the AR1 has the lowest average shortest path across the network. You see there, 2. Followed by AR3 and AR2. The combined network has the longest shortest path, implying that the actual scope of the results of the combined network was longer than for the other networks, hence contributing to why it was a bigger network. So we see that there's some trend that the scope increases from AR1, 2, 3 to the combined network. Now, what about density? Sorry about that. Interpolation wasn't mentioned or seen in the method descriptions. They didn't say anything about whether an analyst should interpret or not. In terms of partitioning, and we look at the method feature here, here are some more quotes from Derek's paper. For the traditional method, the events were categorized into what the analyst thought was relevant. This means that it is likely that there was information relevant to the accident that was discovered, but not included in the results. For SWOT, there were 5 elements of the organization that the events needed to belong to. These were, and these elements are listed there, these were more granular than AR1, but still may have discovered information and then discarded it. For multiple stories, no filter was placed on capturing event information. Whatever information was discovered was captured verbatim. AR1 appears therefore to have the lowest granularity, then AR2, then AR3. Now, in terms of the code distribution, now here we look at a measure of how uniform a histogram is, which is called the Shannon entropy. The Shannon entropy, and thus the granularity of partitioning, increased from AR1 to AR2 to AR3 to the combined network. Increasing Shannon entropy means it's tending towards a more uniform distribution. Now, if we look at the network evidence for density, we looked at some examples on the previous slide showing how the density approximately increases from AR1 to AR2 to AR3 to the combined network. But some useful information to know is out of the 55 nodes of the combined network, AR1 contributed 2 unique events, AR2 8, and AR3 21. This supports the argument that AR3 is the densest of all 3 contributing networks, since it filled in most of the nodes of the combined network. So what do we do with all this? What explains the increasing richness from AR1, 2, 3 to the combined network? The scope of AR2 and AR3 was larger than AR1. AR2 and AR3 scopes were similar when you consider their number of codes and the average shortest path across the network. So the scope is not enough to explain the increased size in terms of the number of nodes of AR3 compared to AR2. But the density of AR3 was greater than AR2 when you consider the Shannon entropy of the coding distribution and the visual test of looking at AR3's contribution to the combined network. So it had 21 unique nodes, unique events, and how these events appear in between AR2 events, as we looked at on the previous slide. It appears as though the increased granularity of the partitioning of AR3 generated this increased density and thus increased richness. What about the combined network? I think that the lower granularity of AR1 and AR2 compared to AR3 enabled unique events to be generated from them, thereby adding to the 45 events of AR3 to get to 55 nodes in the combined network. See, there were 45 events in AR3, and there were, between AR1 and AR2, they had 10 unique events together. Add them together, you get 55. One reason why AR1 and AR2 still contributed unique events in spite of AR3's wide scope and highly granular partitioning is possibly because of their narrower partitioning. They focused on particular areas, and there were details AR1 and AR2 picked up that AR3 didn't. Therefore, the combined scenario, though it had the same scope as AR3, was denser and hence richer. So what are some interim conclusions from this second part? Methods that have a wider scope produce richer accident descriptions in general. Methods with a higher granularity of partitioning produce richer accident descriptions. If you use categories at all to classify events, such as in AR1 and AR2, compared to not doing that, which is in the multiple stories, you may be cutting out relevant information in principle, artificially reducing the richness of the description. Methods that allow or encourage interpolation also tend to produce rich accident descriptions because they increase the density. We didn't directly identify evidence of interpolation, but this point still stands. In terms of combining networks to increase richness, combining networks from methods with different scopes produce richer descriptions. This perhaps is self-evident. AR 1, 2, and 3 had differences in their scopes, and that was reflected in different kinds of events appearing in the combined network. Combining networks from methods with different granularity of partitioning produces richer descriptions. When choosing multiple methods to use together, choose at least one of them that has a lower, more focused granularity than the other. And finally, in general, using causal networks to study accident investigations is a technique that allows easy and clear comparisons between multiple descriptions of the same accident. So what more can be done with them? Our future work will explore this. And if anyone's interested in finding out more or being involved, please let me know. I'd be very keen to chat. Thanks very much.
All right, Ben, well, thank you very much for a very interesting seminar. We have opened up the Q&A, and Ben, I'll pass on the questions to yourself. If everyone can pop your questions in, we've got a good 10, 15 minutes for questions. So please put in your questions into the Q&A. So Ben, the question is, after the actions have been identified, was there any difference in what actions were selected to be implemented?
Derek's work, I didn't go that far, so I don't know the answer. Yeah, sorry. Sounds like I'm cutting you off there, but no, the extent of his paper was just looking at what was generated rather than what was selected. But no, that's a very good point. Obviously, you're right. It's the follow through which matters.
Yeah, I think that's absolutely the point here. It's great to do the analysis. It would be interesting now to go and have a look at what actions were taken and whether they actually resulted in an improvement.
Yep, absolutely.
Right, Ben, at this stage, we haven't got any more questions online. I'm pretty certain people are busy typing madly to get a question in. So what I will do is just pass to Rick. I see your hand popped up there, Rick. I don't know if you've got any questions.
I've got a question, and it's really born out of complete ignorance. But I was fascinated by the complexity of the sort of causal diagrams that you put together, and I'd be interested to know what sort of training is necessary in order to be able to carry out that sort of analysis.
You got to be able to read and comprehend English and use Excel and a bit of MATLAB, and that's it. It's very easy. All we did was you take a paragraph from the report and you identify, you identify what are the key events out of that, and you start linking them together, like literally in Visio on a page. You translate that into make an adjacency matrix in Excel. You import into MATLAB. Bob's your uncle. There you go. It's very straightforward. Yeah, it's very straightforward. And you don't just have to apply it to accident reports. Anything which is focused on describing something causal, you can do that for. So for HAZOPs or for any sort of proactive risk assessment, you can use these techniques. That's actually the other half of my research, which is how can you use causal networks and the various metrics and things you can measure from them to enhance risk management ahead of time. Does that answer your question, Rick?
Yep.
Yeah, Ben, I think you described that so quickly and you made it sound really simple. I probably would quite like to see it in action. I'm not sure it's as simple as you make it out to be.
You're probably right, Neville. You're probably right.
I suppose
I was just thinking, you know, as you were saying that, you know, playing the minute waltz is easy. You just move your fingers really fast up and down the keyboard, and
That's it.
yeah.
That's it. Yeah. Sorry. Yeah. Good point. Good point. Good point. Sorry. The point was, in principle, you don't need any particular special training.
Yeah.
A little bit on the actually generating the diagrams, but in terms of generating the information, that's I've done that. I've had a bunch of first-year engineering students building these networks for me from accident reports successfully, without much guidance. So it's fine.
Yeah, and I think that then just really picks up on the follow-up question, which was very much around, you know, if you looked at the different methods that you've compared, you know, what are the resources and the training needed to apply them, and how,
okay.
you know, I suppose it's a question of how easy is it for people on sites to be able to use these different methods, because everyone would like to have a much better outcome from the investigations, and yet I suppose focus on the tried and tested and the ones that they've been trained on. How do we get a broader distribution, or maybe be able to introduce these other methods?
Do you mean the investigation methods?
Yeah. So you've got your AR 1, 2, and 3, if I'm understanding the question correctly. And you know, what are the skills and training needed, and what resources do you need for that?
So I think it's important to separate the causal network analysis stuff from doing the accident investigation work. And the three methods, the traditional, the SWOT, and the multiple stories, definitely in the accident investigation workspace. And actually using and implementing different methods in that space is very much influenced by the complexity of real work. So for example, if your work says we're going to use SWOT, or we're going to use ICAM, or we're going to use whatever, you have to use them, right? I mean, there are real complexities there. I'm not trying to circumvent or get around. We were trying to look at how you would compare these things, how you would compare those results, and what might be some reasons why they might generate different kinds of descriptions. If your question is how do we implement different investigation methods on site, I think basically the first step is to find a manager who's supportive of the idea, I imagine, and to be able to go in with it, into it, saying with some evidence from perhaps from somewhere else that using multiple different methods together can give you a richer description. And I hope that some of the work we're doing will help to contribute to that. Provide some evidence that if you use more than one, integrate their results, you get a rich description. Now, richer doesn't necessarily mean better. It generally does, I think, but as was pointed out to me 2 weeks ago by a colleague, summarizing accident reports in the right way is extremely important for identifying what are the best actions that come out of it. We were just doing the first step of that, which is saying, how do we just generate more? The next step would be to say, okay, we've got all this information. Is it in the most useful form? How do we best summarize that or combine that to be able to come up with the best actions, which is a separate question. Does that answer your question?
Yes, absolutely, Ben. And there's a follow-up one here, just in terms of the study. Is it possible that there is some carryover from extracting the data via one method to the other method? So that's question one. And then, of course, the one that's really important as well is, so how repeatable? So how easy it is to repeat the results. If others do the same study, would they come to a similar conclusion?
Can you just ask the first part of that again?
All right. Is it possible that there is some carryover from extracting the data via one method to another? So in doing the study, if the same person used all three methods, is it possible that they've learned from the one and put it into the other one, etc.?
Oh, I see what you're saying. That That in terms of Derek's work, or in terms of my work, the second part?
Well, Ben, I think I'm going to say both, because I can't contact the person who's asked the questions.
Sure. Like, I can't speak for Derek's work. I imagine there might have been. They were based on the same basic set of information. In terms of the approach that I took to generate the 3 networks from the 3 accident reports, each accident report I dealt with separately, and I used that as my data source, and I just took the descriptions of each event from each of those reports. So those were kept quite separate. Yes, I can't speak for Derek's work. Now, the second question, Neville.
So the second question is, if we were to get somebody else to do exactly what you did, how repeatable would the results be? Would they be similar? I mean, assume they've had the same training and everything. If you got a handful of people to do the same study, would they come to a similar result?
I think the answer would be yes. The method of extracting the events from the accident reports and for building them into a network, there would be some room, there is some room for variability, but because the method is fairly simple for doing that, and that method is described in a conference paper that's already been published, then you would be able to tell pretty quickly if there was much deviation. So, for example, I think it would be fairly similar. I think you would certainly see the same trend.
All right, and I think we've got time for one more question. And Rick, I see you've got your hand up. If you've got a burning question, please put it in the Q&A. If you do have questions, because I'm just cognizant the last couple of webinars when I've gone into the wrap-up, suddenly I've got questions. If you do have questions that are outstanding, please feel free to email Ben or to pop the questions on the Q&A, and we'll pick it up and get back to you as soon as we can. So Rick, you've got a question, and then I've got one more online.
Yeah, I guess this is a question that follows on from the one about reproducibility, and if you think and I guess your answer was you thought that if you had somebody else coming in and looking at the same incident report, that they would come to similar conclusions. The question that obviously follows on from that in the current day and age is, can we teach a machine learning, artificial intelligence routine to do the same thing, particularly in light of the fact that, one of the bits, I've had very little connection with this, but the one bit of connection I've had was, a whole group of industry representatives saying, wouldn't it be wonderful if we were able to share analyses of incidents more kind of rapidly in a standardized way. And so my question is, I guess, could you think it would therefore be possible to teach some sort of machine learning, natural language approach to analyzing thousands of these reports in a standardized way? That would be would it be of value?
Yes, I think it would be. I'm not a machine learning person or an AI person, right? But from the little I do know, I think absolutely. There are a plethora of accident reports about many systems all around the world, and to be able to mine that, to be able to compare and extract what are the similarities so we can learn from them, A, would be a worthwhile endeavor anyway, but B, I imagine it will be very doable. The benefit of using the network approach that I've done here is that comparing them is made really easy once you're in that format. The natural language processing part to get to that point, I don't imagine would be difficult for an AI specialist to build. But certainly the comparison becomes very easy once you've got it in a network format. You can do a lot with it then. So yes, I think the answer is yes.
So I think, well, the last question, I'm going to say great minds think alike. So
sorry about that.
Changwan Son from Texas A&M University has pretty much asked the same question, and it was really around, assuming you draw the arcs and you identify the nodes, and that depends on who's doing the analysis. could AI or machine learning be a solution to address the subjectivity? So Chang-Won, thanks for the question. If you have any ideas, we would love to have a chat with you. I think it's a great idea. And with that, I think I will bring the webinar to an end and just thank Ben again for putting the time aside to come and chat to us and share your research. I always find these webinars incredibly interesting because I get to get a greater and greater insight into all the fantastic work that's been done across the Institute. We will be following up next week with a seminar at the same time. So if you'd like to pop that in your diary, we will send out the details of the speaker later in the week. But otherwise, welcome back, and look forward to seeing you all again next week, Tuesday at the same time. If you have missed the seminars, please, they're on our website. You can access them there. And we look forward to comments and emails and suggestions. And once again, if there are any particular topics you would like covered, please let me know. We're very happy to get a researcher either from SMI or from our network around the world to tackle particular subjects if they're of interest to you. So Ben, once again, thank you very much. And Rick, thanks very much for setting everything up. Goodbye, everyone.
No worries. Bye.